Hello and welcome to chi-squared tests. We have goodness of fit, homogeneity, and independence. So what is this all about? This is, I forget what chapter it is. I think it's chapter 25 in our textbook, in our Pearson textbook. But anyway, like back in the day, we had contingency tables and we were trying to talk about independence and trying to say, well, things are independent or they weren't. And we were very strict about it. Either all the probabilities were equal or they were not. And we said if they were equal, then they're independent. If they're not, then they're not. But we know that in real life, there's natural variability going on. So now we're going to be talking about the same kind of idea, checking to see if things are the same or if they're different, kind of like we did with the contingency tables back in the day. But we're going to allow for a little variation, natural variation to it. Okay, so before I get too far into it, there are three types. Independence is kind of the idea we're used to with contingency tables, either, probabilities and proportions being exactly the same or not. But there's different types. There's goodness of fit, which we're going to look at first, homogeneity and independence. So goodness of fit, let me pop this up. Maybe this is a better picture. Here it is. Okay, so this kind of gives a general picture of the three different types. So, goodness of fit, what you're doing is trying to compare an expected number of counts to what you have in front of you. So, for example, you would imagine that, star signs or, birth signs like Virgo, Aries, Leo, blah, blah, blah. You would imagine those would be evenly distributed throughout the population. But until you check it, until you test it, you don't know for sure. So you can go out and you can find a bunch of people and you can say, let's just say you go and find 12 people. So since there are 12 star signs, I think there's 12, right? If you find 12 star signs or 12 people, you would expect that you'd find one of each on average, right? Of course, it's not going to work out if you just find 12 people. So let's say you do 60 people, right? And if there's 12 star signs, that means that you would expect to see five of each in each of the star signs. So what you're doing is comparing what you're going to observe from your sample to what you expect based on probabilities or just based on the distribution, right? You would expect that the Virgo, Aries, Leo would all be the same. So if I survey 60 people, I would expect to see five of each, right? And that's what you're going to compare. For homogeneity, you are doing two groups, and we're going to get into each one of these separately, but I'm trying to give you a general overview to begin with. So you're going to group people to begin with, like males and females, or could be old, uh, I don't know, an old dogs and young dogs, or whatever. And it doesn't have to be two groups. You can have multiple groups. You could have, I think we're going to see a problem, or there's a problem in the homeworks, like engineers and like different businesses and colleges. You have engineering college and business college and the arts or whatever, and have these different colleges. So, but the main point is that you're going to group them first. So you already know what groups you're interested in looking at. I want to have freshmen, sophomores, juniors, and seniors, and I'm going to make sure I go and survey each one of those groups. So the groups are made ahead of time. You can decide how many you're going to choose from each group, and you can make them the same or not if you want. And then you're going to like survey them, or you're going to do an experiment on them or whatever. Like this kind of shows here, like you're giving them a drug or something, and you can see whether they're cured or partially cured or not cured at all, right? Okay, but you are choosing the groups ahead of time. And what you're doing is just trying to say, well, between these groups, did the distribution of cured, partially cured, and not cured, are they equal? Because within this group, you're going to have each category: cured, partially cured, not cured. And in this group, you're going to have the same thing: cured, partially cured, not cured. Same thing here, same thing here. So for each group, you get all those different choices. So a lot of this you can look at as part of like a variable. So in this case, we only have one variable. The groups were not a variable. They're just groups I'm interested in. The variable is whether they were cured or not, or partially cured. So we have one variable. Sorry, when you get to independence, there are two variables. You don't make groups ahead of time. You just go and you randomly select people from one population, and you will find, or you are interested in, two variables within that population. Maybe your smoking versus heart, your how good your heart is, right? So do you have heart problems, or have you had a heart attack, blah blah blah, and you're trying to do some kind of link between smoking and non-smoking and heart problems, right? But the two variables, one variable would be, do you smoke or not? And the other variable would be, and to what level. Like, you can actually make this a number and say, I smoke a little bit, I smoke a medium, I smoke a lot, right? And you can make that some one variable. And then you can make the level of heart problems a variable as well. So you have two variables coming from one population. These are not grouped. Okay. So independence has two variables, homogeneity has one variable, and goodness of fit, I guess you call it a variable, but really it's comparing counts. So it's not really even a variable, really. It's just kind of comparing. I mean, it is, but you're kind of comparing counts from what you see to what you expect. And what you expect is known ahead. Well, let's get into the details, shall we? Okay, so that's general kind of rule. One variable, two variables. This is many different groups, where this is only one group. All right, that's a good overview. I like this picture. It kind of gives you an idea of, like, when you're trying to decide which it is. We'll come back to it. Okay, so let's get into goodness of fit and those kind of things. I just talked about all that. They have to be counts, so you're looking at how many of everything for a goodness of fit test, right? And here's our conditions. So they need to be counted data, and you're not doing like continuous data. It's discrete, kind of. You're counting how many people are in this category, how many people are Virgos, how many people are Leos, how many people. It's a count. Okay. They need to be random and independent, like normal. So we're still going to use IRS, right? I for independence and R for randomness. And then our S, our sample size, turns into an expected cell frequency. So in each of our expected cells, not the observed cell, but in the expected cell, you have to have at least 5. All right, so it's still IRS. The 10% condition still is hanging out, but like always, the 10% condition is really not the main concern. So this is fine, IRS. And you have to add in that it's counted data. Okay? It's not going to really all gel until we kind of get to it. All right, so before we get too far into a problem, I do want to talk about the distributions. So in the past, we've had Z distributions, right, which is just a perfectly normal curve. We've had T distributions, right, which are like a normal curve, but they allow for a little more air. So the tails are a little fatter and the middle's a little more shallow. And then now we're going to be talking about what's called a chi-squared distribution. And this is supposed to be the Greek letter chi, and then we say chi-squared. Okay, so this is a chi-squared distribution. So it's just a brand new distribution. Right, so when we do a test, in the past, when we did a test for proportions, we looked for a z-score, and we tried to say, how unusual is that z-score? Right? And then we moved to means and we did a t-score, and we said, well, how unusual is that t-score? And they were very similar. Maybe for a z, you might get 1.96 for 95%. But for a t, depending on its degrees of freedom, we ended up with different numbers. It depends. You get maybe 2.07 or something. It was close to 2, though, right? Well, chi-squared is going to do something similar um, as the z and the t does. When we do a chi-squared test, we're going to be looking for a chi-squared value, just like we did with z and t. And we're going to have some measure, some model that we can use to come up with a probability, just like we did before. And we get our p-value, and then we can either reject or fail to reject the null hypothesis. So it's the same thing, same process, pretty much. It's just that we have this new distribution now called chi-squared. All right, so what's a chi-square distribution look like compared to the other two? Let me zip all the way down here first so I can show you. Sorry, I'm jumping around here a little bit, a lot. Okay, so these are chi-square distributions. In general, they're kind of skewed to the right normal curves, kind of. You can see the degrees of freedom on the right over here. So if you have 1 degree of freedom, it's actually kind of a strange curve like this coming down. 2 degrees of freedom here in green, right? When you get to 3 degrees of freedom, then you start to look kind of like a normal curve, but they're very much skewed to the right, right? And as you get bigger and bigger and bigger, then they start to level off a little more. They're always going to be skewed to the right, but they start to kind of level off a little bit more. They get really wide. You'll notice that there's a number down here. That number is chi-squared. That's our chi-squared number that we're going to be looking for. So we're going to say stuff like, well, let's say we have a chi-squared model with 4 degrees of freedom, which is this blue one, right? And then you're going to do a calculation for chi-squared. And let's say you get a chi-squared of 5 from your sample, right? So we're going to look at this blue distribution, right? And we're going to say, how unusual is it to get a value of 5 for chi-squared, given that we have 4 degrees of freedom on our model, right? So that's very similar to what we did before, right? We said, let's get a t-score, a z-score. And if our z-score was unusual or our t-score was unusual, then we can reject or fail to reject. So we're doing the same thing, same process. It's just a different model. And our cutoffs now are going to be a little different than what we're used to. We're used to like 2 being unusual or 3 being really unusual, right? But now it's going to be different. It's going to be a chi-squared value. Okay, so let's back up again. What's a chi-squared value then? If it's not the same as a z or a t, what is it? Well, it comes from the idea, it's kind of like a standard deviation. You know, when we did standard deviation, you'd take your value that you have, like all the values in your data set, and you would subtract the mean from them to get a residual or get a difference. And because some of them are positive and some of them are negative, we'd square these so that we'd end up with all positives. And then we divided by like n minus 1, right? Well, we added them together, right? We summed up all those little residuals squared, and then we divided by n minus 1. This is so similar to what you're doing here. You're taking what you observe, right? Same thing as this, subtracting what you expect, which is kind of your center, right? The the center is the expected value. And when you subtract those, you sometimes you get negatives and sometimes you get positives. So again, we're going to square it, right? And we're going to get that residual squared. And then to normalize it, to figure out like, to turn it into a kind of a z-score, we're going to divide by what the average was again. So we're going to divide by the average. This is a little different because we took an average before. But now we're going to divide by the expected value to get a z-score. So this formula, it's similar to a standard deviation, but to be honest, it's more like calculating a z-score. So you're going to end up with a whole bunch of z-scores. And it's just that you square it. And that's maybe why the squared comes into it. It's not really a z-score. It's kind of like a z-score squared. And then you're going to add all those z-scores together. Because if you think about it, if we go back to this, sorry, let me get rid of that junk. If you go back to this, we're not just looking at one number anymore. We're looking at a whole category versus of numbers. So you're going to get a z-score here, a z-score here, a z-score here, a z-score here. And then that's going to be kind of squared. The residual gets squared. And then those all get added together. And so you end up with this bigger number. It's like a z-score of 2 plus a z-score of 3 and a z-score of 1.7 plus a z-score of another 2, right? Or whatever. So if you have like 4 categories and it's something that's unusual, you could get a whole bunch of like 2 plus 2 plus 2 plus 2s and get like a z-score, or sorry, a chi-squared of like 8, right? So that's why that chi-squared number is bigger, because it's like doing a z-score on a whole bunch of different categories at once and adding them together. You're summing them all up. All right. Again, it's not going to really make sense and sink in until we do some problems, right? So let's do some. Yeah, let's just go right into the homogeneity. So let's try a homogeneity or goodness of fit problem. I mean, sorry. I got one here. I just took this from the textbook, and this is about fruit flies. And with goodness of fit, there's always some kind of expected ratio or proportion or count that we expect. It's called the expected count for a purpose. You expect to see this if things were perfectly the way you thought they were supposed to be. If you roll a dice 6 times, you expect to see one of each. If you roll a dice, 30 times, you expect to see five of each, etc. So it's the expected count we're looking at and trying to compare to. So they go and they say, well, you can they sorry they sample 100 fruit flies. So they go and say, let's find these fruit flies, let's sample them, and they say they have these bodies and wings, different colored bodies and different sized wings and things like this, right? So from the different traits, and they have like yellow normal, yellow short, ebony normal, and ebony short, right? So the counts they see from their sample are 59, 20, 11, and 10, right? We have to figure out what we expect to see. So from our sample of 100, if this is the proportion we're talking about, 9, 3, 3, 1, that we expect to see, out of 100, what does that turn into? All right, so I've kind of set it up on my calculator already for us. We got fruit flies, all right? And I did the calculation, but I'll show you how it works. So this 59, 20, 11, and 10 is what we observed from our sample of 100. We expected to see a ratio of 9, 3, 3, 1. This is like, if you add those up, that's only what, 12, 15, 16, right? So out of 16, how I got to convert that to a sample of 100. Okay, so I got to get the proportion. So I did the math over here. I took 100 divided by 16 to say, like, well, how much would it be if it came out to 16, and like for per part, and then I had to multiply it by its part. So if I took 100 and I distributed it into 16 parts to match the 9, 3, 3, 1, then this is what you would get: 56.25, etc., right? 18.75, 18.7, and 6.25. Okay, so you kind of have to do the math on that yourself a little bit to say, all right, I got to convert this ratios into an expected value. Before you can do any kind of chi-squared, you got to have your observed and you got to have your expected list. Now, a goodness of fit uses two lists, and it's always just two lists: what you observed and what you expect in two lists, and that's it. All right. When we do the other test, the homogeneity and the independence, we won't be using two lists. We'll be using a matrix, and I'll show you that in a minute. Okay, so what are we asking? Well, we're asking that, if this is what I observed, does that follow what I expected? 56 to 59 is a little different, but is it so different that I think something's like that I think my expected is wrong? Or is it just because of natural variation? Maybe it really is 56, but I got 59 just because it was this particular sample. If I took another sample, it would be closer to 56, or it'd be even a little bit below, right? So how unusual is this is what we want to know. 18 to 20 isn't that far off. I'm noticing here though, 18 to 11, that's pretty far off. That's more than 7 away. Well, more than 7 away, right? And then 6 to 10, it's a little bit off, but not too bad. So I'm just curious, like, does this distribution match this distribution? You know what I mean? So let me go back to the notes real quick to kind of stick this in your head. This isn't exactly what you're doing, but it's close. Sorry, I'm going the wrong way. I'm looking for this graph. Yeah. Now this is more for when we do chi-squared of independence. So, but I'm just going to use it right now to make a point. Like in the past, we said these distributions and these proportions had to be perfectly the same Otherwise, we weren't going to say they were independent, right? But we know there's natural variation. So the question is, how different can these be before we start to say that they don't really match anymore, right? So that's kind of what we're getting at here. Whoops. How far off is far enough that I start to think this distribution is wrong. Okay, so the expected kind of becomes your null hypothesis. This is what I think is going to be happening. This is what I think is true. That's your null hypothesis. And then this becomes your, well, it is your sample that you're testing against the null. But it's the whole, like all four numbers together is your null, right? It's not just one number anymore. It's a whole set of numbers. Okay, so how do you calculate it again? Oh yeah, you have to take your observed minus your expected. That gives you kind of some kind of residual. You square it, right? Then you have to divide by the expected again to turn it into kind of a z-score, kind of. It's a normalized kind of number. And then you add them all together. So you do that for this one, this one, this one, this one, and you put them all together. So I'm going to write that maybe right here on the screen to show you what it would look like. So if I were doing it by hand, I would go chi squared. And by the way, how many degrees of freedom do I have? I have 3 degrees of freedom. How did I get that? You take your sample size of 4 and subtract 1 from it. So it's n minus 1 for a goodness of fit. So this is 4 minus 1, which is 3 degrees of freedom. So that's how you're supposed to write it. Chi squared with 3 degrees of freedom. I would take like I said before, you take your observed, 59, subtract your expected, square that number, whatever that is. Sorry, this is a little messy. Then divide by your expected again to normalize it. And then that's the component for just this first piece. Then we have to add on the same thing for the rest. So you would do that over and over and over for every single piece until you get to the last one. And I'm just going to do the first and the last. And you see I put a dot, dot, dot in the middle to show I'm just repeating the same pattern. So let me just do the last one. 6.25 is what I expected. And then I got to square. That's a difference, like a residual. And then I got to square that and divide by the expected. Well, that's getting really messy. My computer's getting jittery right now. I can feel it. Okay, so I would just do the first one, write it out, get the last one, and then that would be how you would calculate chi-squared by hand. When you do a test and you write it up on a free response question, you have to show this. You have to show this calculation. You don't have to write them all up, but you should write 2 of all the different ones that you have. You have to write at least 2 of them up. A lot of times I just do the first one and the last one and then do a dot, dot, dot in between in the middle. Okay, let me erase that and then go back to the calculator will do all this for you, right? But you have to show your understanding. So that's how you show your understanding. Okay, so let's do the goodness of fit test. Statistics, stat test. You see down here, there's a chi-squared GOF. That's goodness of fit. So chi-squared GOF, that's goodness of fit. Observed lists. That was my fruit flies. My expected list, I just named it expected, so it wouldn't be confusing for me. And I said I had 3 degrees of freedom. So you have to tell them you have 3 degrees of freedom. Okay, I hit OK, and it will do my chi-squared test for me. All right, so that chi-squared value, let me go back here, show you the formula again. All right. Whoops, right there, right? Observed minus expected squared over the expected. So this is what you're doing, summing them all up, right? So the calculator does that. It gives me 5.67 for degrees of freedom of 3. Remember, I have, for 3 degrees of freedom, it's really far over to the left, and then it skews out to the right. So that's the type of graph I would be drawing. The center of this, just to let you know, is always going to be 2 less than your degrees of freedom. So if I have 3 degrees of freedom, I know this is going to be centered at 1. So 0, 1, 2, 3, 4, 5. I can see that 5.67 is out here kind of a ways, it's out here somewhere, out here somewhere. I probably didn't draw my picture very well because I can see that my probability for that area is actually quite large. I mean, it's 12.9%. That's fairly large, right? I made it look really small in my graph, but it's really a little bit larger than that. So this is a chi-squared model for 3 degrees of freedom, right? And then normally I would just kind of somewhere I would draw that 5.67 cutoff and then shade that in. But just make sure you label that as like, oh, this is 5.67, right? 1, 2, 3, I don't know, 4, 5, 5.67. I'm making it really messy, but that's kind of the idea. Just like on a normal curve or a T curve, that's how you draw it out, right? The rest is pretty much the same as far as the null and the rejecting or don't rejecting. So my null is 12.8%. 0.128 is large. That's higher than 0.05. I failed to reject the null, right? The null is that this is the distribution. So I failed to reject that. I still believe that this is the distribution of fruit fly bodies and wings. Just because my sample was a little off from that doesn't mean that they're wrong, right? I mean, that's always true, but I don't have any reason to believe that they're wrong from my sample. Is it a little off? Sure. Is it enough off? No, it's not that far off. Why? Well, because my chi-squared and my p-value told me so, just like before. Okay, so just like z's and t's, all that. The only thing I'm going to add on here is, remember this chi-squared came from different pieces now. We had 4 pieces, not just one piece. Not just like in the past, we had like one mean from a sample, right? Maybe at the most we had 2 means and we compared them. But here we had 4 components. So what you can do, you see this right here, it says component list. You can scroll up there and look at it and stuff. But what I do is what you need to do, or what you can do, is go to this variables button on your calculator, hit the variables button. And for whatever test you did recently, the most recently, it will populate this list of stuff. So right here it says component list. So I'm going to click on that, hit enter, and it will give me those 4 components. These are the chi-squared values. These are the chi-squared values, right, for each of those. You know how I started writing out the 4 different ones? I wrote the first one and I wrote the last one. That's what this is giving me. It's giving me those 4 values. So this chi-squared comes from these 4 values being added together, right? 0.13 plus 0.08 plus 3.2 plus 2.25. Those added together give you that. Each of these is like a z-score, right? 0.13, that's not very unusual for a z-score. 0.08, that's not very unusual either. 3.2, yes, that is unusual for a z-score. So I can tell right away. Remember how I talked about that third value? Remember I said this one was pretty far off, where the other ones were pretty close? This is really off, so it shows up in the component list. It shows up here as a z-score that's really large. So that one component is actually pretty unusual. But it's not enough to say the whole distribution is off, right? Same with this one, 2.25. That's pretty unusual as well. It's not crazy unusual, but it's definitely unusual. 3.2 is definitely unusual for sure, right? But the way chi-squared works is the whole distribution has to be off or it just isn't going to show up, okay? Just one of the components isn't enough. Okay, so that's where chi-squared comes from, and that's really some good insight there. Think of these as z-scores. Chi-squared is like a total of all the z-scores added together to give you a general idea of all, like how unusual the whole set is together. All right, I hope that gives you a really good base. So that's goodness of fit. I won't talk as much on the other two. Let's do two more examples for the other types. The other types work almost the same way, except we're going to use a matrix instead of a list. Okay, so let's do those two other problems real quick. Okay, so that was the fruit fly. Say that 10 times fast. Okay, let's go to a homogeneity test. Homogeneity. Let's remind ourselves, homogeneity is the one where I already have groups. I've already decided I'm going to survey freshmen, sophomore, juniors, and seniors, or, young women, old women, young men, old men, something like that. I don't know. Whatever your groups are, you've already decided on the groups, and you have one variable that you're going to measure. Okay, so that's homogeneity. Let's look at a homogeneity problem. I gotta find it. Sorry, there it is. Again, I took this from a book. This is like number 39 in the book. And what it is saying, well, we have two professors, and this is their distribution of grades, right? And we want to know, does Professor Alpha and Professor Beta give different grades? Is there an easy teacher and a difficult teacher, or are they pretty much given the same grades, right? Kids complain about that kind of stuff all the time, right? Okay, so you can use chi-squared to figure that out. Okay, so here's our two distributions. You want to take those, okay, and I opened up a new document, and what you do is you take those values and you put them into a matrix. So let me show you. When you open up your tools, there's a matrix button here. You can create a matrix. So this one would be a 5 by 2. So I say matrix, I want 5 rows by 2 columns. Hit enter, and then you can put all those values in. All right. 3 tab, 9 tab, 11 tab, 12 tab, 14 tab, right? And continue. Okay, and what I do before you hit enter, you need to name this matrix. So I'm going to do control store. You can see right here, it's hard to see, but right above that variables button is a little blue STO. That means store your variable. So you can tell it where you want to store it. So I did this already. I'll just do it again. I'm going to type the letter A. I'll just say, please store that in letter A. But you can use any letter you want. You can use G, T, whatever. Hit enter, and that'll store it. So now when I hit the letter A, you see how it turned bold, right? Because it knows there's something that's named A. I'm going to hit enter, right? You see how now A has been defined as this matrix, okay? That's what we want. We want a matrix as a letter, okay? So this one, yes, you can go through this whole rigmarole of, trying to figure out what the expected values and stuff would be, but this gets a little more difficult. It's going to be much easier if you just go right to the test. So let's go to the test. And again, before I do any of this, I should have gone through the conditions. Um, but it's kind of a catch-22 because I need my expected values, my expected counts, before I can do my conditions. So I'm going to actually do the test on my calculator first. And in this case, I'm not doing a goodness of fit test. I'm doing a two-way test. So homogeneity and independence use a two-way test, both of them. Goodness of fit is its own animal over here. All right, so let's do two-way test. It just asks you, it's really simple, right? It says which matrix. I say matrix A, and I hit enter, and it knows already that you use matrix A, and it does all the work. Okay, so before I can, I'm like, great, I got my chi-squared, I got my p-value, I could go ahead and just complete the test pretty much. The trouble is I have to go through conditions first, right? I have to write up the chi-squared first. I have to do all that work. So let's go through the conditions. Well, were they randomly selected? Let's just say that these students were randomly selected and I looked at their grades. Okay, sure. Are they independent? Yeah, the grades of students are independent from each other. Okay, and then the sample size, right? That's IR. So for IRS, I need my sample counts, my expected counts. Sorry, not the sample from your not these numbers, right? I can see here this is like 1, 2, and 3 right here. That's not what we're looking at. We're actually looking at the expected counts. So the expected counts have to be 5 or bigger. Well, it says expected matrix right here. How do I get to that? Well, same way. You go over here to this variables button, you hit variables, and you can see right here, it has an expected matrix. So I hit expected matrix, hit enter, and you see all that comes up. These are the expected counts for this distribution. You see how it went 3, 11, 14? So here I would expect it to be 6, 12, and 12, but it's 3, 11, and 14, right? A little different for sure. 6, 12, 12, 3, 11, 14. Okay, so that's what the chi-squared is comparing. It's comparing these numbers to the expected. This is what you think it's going to do. Now, the good news is you don't have to calculate these yourself. The calculator does it for you. All you have to do is write these numbers down on your free response question. And yes, you have to write them all. So you will write these numbers down. Yes, you can round them a little bit for sure. I would just go 6.6 and 5.4 and 12.6 and 10.4, right? And write those down on your free response question. Then you would check those with your sample size and say the expected counts are bigger than 5 or equal to 5. But take a look at this. There's a problem. For this particular one, you can see that this does not meet the conditions. My expected counts are not bigger than 5. I would not continue with this test. All right, you'd have to stop. You can't do it. It's not appropriate. All right. What they do in the textbook is they go and they say, okay, let's do a workaround, and they say let's make this category together. So we'll have an A, B, C category, but we're going to have a less than C category. So then they put these together into 12, and they put these together into 3. And if you do the matrix on that, it actually solves the problem, and you can continue with the test. The trouble is you don't have a D and F category separately. You just have a D and F combo category, which is fine. You just have to interpret it properly, though, right? Okay, so let me just to save time. What if we did continue with this test? What would I be saying? Well, I would say, here's my chi-squared. I have a p-value that's bigger than 5%, just a little bit, but it's bigger. So I would fail to reject the null, and I would not have enough evidence to suggest that Professor Alpha and Professor Beta have different distributions of grades. I would have to say there's evidence to suggest that these distributions are the same or very, very similar. All right. Obviously, they're not exactly the same, but that's just because of natural variation, right? Okay. Again, let me just go to the beginning. How did I know this was homogeneity? Because I have two groups that I already had set. I knew I was going to sample from these two groups, and I have one variable. This distribution is my one variable. Okay, so let's move on to independence. What's independence look like? Whoops, wrong one. Independence is that you don't have predetermined groups. You only have one population that you're pulling from. I'm going to pull students from ASIJ, and I'm not going to predetermine what grade level they're in. I'm not going to predetermine what sex or race they are. I'm not going to predetermine anything. But I might ask them two questions, right? I'm going to ask them, what's your GPA and how many hours of sleep do you get per night? And then I can compare those and see if they're the same, right? Um, or whatever, right? And I can put those into groups. Sorry, I didn't want this. I wanted my question. So let's take a look at another problem here. This one. This is another problem from the text. Sorry, someone's trying to get in my room right now, but I got it locked because I'm doing this video. Sorry, I'm just looking. Okay, so this one is childbirth, and they're talking about if you get an epidural or not, and then also breastfeeding. Are you having trouble breastfeeding or not, right? Up to 6 months kind of thing. The whole premise is that if you get an epidural when you're having your baby, then the baby gets a little bit of that medicine in them, and they are sleepier, and they're less willing to breastfeed. So that's kind of like what they're asking, right? and whether the baby is still nursing after 6 months, right? So that's what they asked them. Okay. It's kind of funny that this question comes on today because just today, if you guys know Miss Ortwine, her and Mr. Jacobson just had their baby today, like just a few hours ago while I'm doing this video. Here's a picture of their brand new baby that they just had 3 hours ago. Ha ha ha. Cool. It's cutie, right? Looks like Mr. Jacobson. Anyway, I thought that was appropriate that we're doing this question at this moment. But anyway, let's look at the data. This is an independence question. She's going to kill me that I put that on there. She probably doesn't want it up, but I put it anyway. Anyway, so this is the independence question. How do we know? Because we just randomly selected pregnant women and we followed them and we said, okay, did you get an epidural or not? And we asked them that question. And then we went and asked them, are they still breastfeeding after 6 months? So this is all from one group, pregnant women. It's just one group, okay? But I have two variables. This now becomes a variable, and this is also a variable. So I have two variables. That's how I know this is an independence question. All right, that's how I know it's independence. What are the mechanics? Exactly the same as we did before with the matrix. Exactly the same. So let me do it real quick. We're going to have to work more problems in class. I don't want to make this video too long. So I'm just quickly going to do this. I would do a matrix. I need a 2 by 2 matrix. 2 by 2, yes. Let's put in the numbers. 206, 498, 206, 498, 190, 284, 190, 284, I think I said. 284, yes. And I need to store that. Control store. I'm just going to name it C or something. Okay, you can name it whatever you want. You do your two-way test, stat test. This is a two-way test. It's the same test as the homogeneity. I tell it matrix C. I say okay. I get my chi-squared value. I get my p-value. And my degrees of freedom is just 1. Well, where's the degrees of freedom come? We didn't talk about that. This is a 2 by 2. A 2 by 2. So what you're supposed to do is take the rows minus 1 times the columns minus 1. So this is like 2 minus 1 is 1, and 2 minus 1 is 1. So 1 times 1 is just 1. So this has degrees of freedom of just 1. All right, so you take rows minus 1 times columns minus 1, and you get your degrees of freedom. All right, again, I can get my expected matrix, I can get my component matrix, and I can then get all my stuff that I need, right? I have to check the expected matrix to make sure the values are 5 or greater for my conditions. When I write up my test, I have to write out 2 of those chi-squared components by hand, and then I can show my understanding. But after that, you can just give the chi-squared value and the p-value, and then you can interpret the test. Okay, we'll practice more of these problems in class. Hopefully you just understand the difference between the 3 tests, and you also understand how the calculator works a little bit and how that's supposed to work so that you can kind of get going on the problems, right? So let's look at the details in class. Thank you very much.